Dear students, myself K. Lakshmi, working as assistant professor in Narasimha Reddy Engineering College. So today you are going to study about feedback amplifiers. In feedback amplifiers, that is Unit 2. So let us see first topic, classification of amplifiers. So depending on the magnitudes of input and output impedances with relative to source and load impedances, we can classify different types of amplifiers. So before moving to the concept of feedback, let us study different types of basic amplifiers. They are nothing but amplifiers can be classified broadly as voltage amplifiers, current amplifiers, transconductance amplifiers and transresistance amplifiers. Okay, let us see one by one like its characteristics. So coming to voltage amplifier, so this is the equivalent circuit of voltage amplifier. So in order to draw equivalent circuit, voltage amplifier, so at the inputs means the figure shows the Thevenin's equivalent of a voltage amplifier. So the Thevenin's equivalent is nothing but equivalent circuit of voltage amplifier. If you see at the input side source is connected and at the output side load is connected to the equivalent circuit of a voltage amplifier, that is nothing but voltage, this is nothing but internal circuit of voltage amplifier. Okay, so here at the input side, so we always compare so input resistance with the source resistance, load resistance with the output resistance. So here you can see circuit is a two-port network and it represents an amplifier. Suppose if Ri is very much greater than Rs, drop across Rs is very small, therefore neglect Rs. Similarly, if RL is very much greater than R0, then we can neglect ideally R0. So in this case at the input side, when Ri is very much greater than Rs, it will act as short. Therefore in that case Vi will be equal to Vs. See, if Ri is very much greater than Rs, then Vi equal to Vs. In the same way, if we take condition as RL is very much greater than R0, so in this case V0 will be equal to AV into Vi. So here from the input side Vi equal to Vs, in the place of Vi if you substitute, V0 will be equal to AV into Vs, where AV is nothing but proportionality factor which does not depend upon the magnitudes of source and load impedances. So here AV represents the open circuit voltage gain. So what are the ideal values of a voltage amplifier? That is Ri equal to infinity and R0 equal to 0. So what are the practical values of a voltage amplifier? So that is Ri is very much greater than Rs, R0 is very much lesser than RL. So this is about voltage amplifier. In the same way we can see the characteristics of current amplifier. So to like the figure represents the equivalent circuit of a current amplifier. So this is nothing but Norton's equivalent. See at the input side, so current source Rs is in parallel with the current source, whereas at the output side also it is, since it is Norton's equivalent, therefore R0 is in parallel with the current source, that is nothing but Ai into Ii. Okay, an ideal current amplifier is one which gives output current proportional to input current and the proportionality factor is independent of Rs and RL. So in the previous slide just now I have explained you, so proportionality factor does not depend upon the magnitude of source and load impedances, that is it is independent of Rs and RL. So here also when do we say Ii will be equal to Is? When Rs is large. That means if Ri is very much lesser than Rs, so when Rs is large, ideally we can assume it as open circuit. Therefore Ii equal to Is. In the same way, when I0 will be equal to Ai into Ii, when R0 is very much greater than RL. So in this condition we can say I0 is approximately equal to Ai into Ii. From the input side, Ii equal to Is, therefore it is written as Ai into Is. So here Ai is nothing but proportionality factor which is independent of Rs and Rl. Okay, so therefore Ai represents the short circuit current gain. So what are the ideal values of a current amplifier? That is Ri equal to 0 and R0 equal to infinity. What are the practical values of a current amplifier? Ri is very much lesser than Rs, R0 is very much greater than Rl. Okay. So next we will see the next amplifier, that is transconductance amplifier. So transconductance amplifier means, in general, what is the definition of a conductance? Ratio of output current to the input voltage. So at the what is the output is current, therefore draw the Norton's equivalent circuit at the output side. Input is voltage, draw the Thevenin's equivalent, means we are drawing the equivalent that is Thevenin's at the input side and Norton's at the output side in order to obtain the equivalent circuit for transconductance amplifier. So here Gm represents the transconductance. Here Gm into Vi is nothing but current source, and here R0, whenever current source is there, R0 should be in parallel with Gm into Vi. So in this way we will draw the transconductance amplifier. So ideal transconductance amplifier supplies output current which is proportional to input voltage. So let us see again here the proportionality constant. What is proportionality constant? Gm is the proportionality constant which is independent of magnitude of Rs and Rl. So here also when we will say Vi equal to Vs, when Rs is very much lesser than Ri. Similarly, when do we say I0 equal to Gm into Vi? When R0 is very much greater than RL. So if Ri is very much greater than Rs, then Vi equal to Vs. If R0 is very much greater than RL, then I0 equal to Gm into Vi. From the input side, in the place of Vi, we will substitute Vs. So where Gm is nothing but proportionality constant, so which does not depend on magnitude of Rs and RL. So here we can say the output current is proportional to the signal voltage. So where Gm represents the short circuit transfer means short circuit transconductance, or we can say transfer conductance. In the same way we can see the last amplifier, that is nothing but trans resistance amplifier. So by definition it is ratio of output voltage to the input current. So output is voltage, therefore draw the Thevenin's equivalent. At the input side you draw the Norton's equivalent. So whenever Norton's equivalent, we must introduce current source. Whenever we will be saying Thevenin's equivalent, there should be the voltage source. Here Rm represents the trans resistance. Okay, so I into Ii. So here it is nothing but R0 is in series with voltage source. Whenever voltage source, therefore R0 must be connected in series with Rm into Ii. In the same way, when Ii will be equal to Is at the input side, when Rs is very much greater than Ri. So if Ri is very much lesser than Rs, then Ii equal to Is, approximately equal to Is. Similarly, when do we say output voltage will be equal to Rm into Ii? When R0 is very much lesser than RL. So in this case we can say V0 equal to approximately equal to Rm into Ii. From the input side, in the place of Ii you substitute Is. Say hence Rm equal to V0 divided by Ii. So here I can say the output voltage is proportional to the signal current. So here Rm represents the open circuit mutual or transfer resistance. So what are the ideal values of trans resistance amplifier? So that is Ri equal to 0, R0 equal to 0. What are the practical values of trans resistance amplifier? That is Ri is very much lesser than Rs, R0 is also very much lesser than RL. So these are nothing but characteristics of basic amplifiers. They are nothing but voltage amplifier, current amplifier, trans conductance amplifier, trans resistance amplifier. So in the next topic we will move to the concept of negative feedback. Thank you.